Yantian is going to do his proposal presentation, and then this also will serve as both his proposal and the comprehensive exam. Unless there are any objections, I would suggest that we let him do the proposal presentation, and then we can do the questions on both the proposal and the comprehensive after that. Okay? Okay. Okay. So Yantian, you can start your proposal presentation. Thank you.
Okay, thank you. Okay. Hello, everyone. Thank you for coming. Today, I will talk about my PhD proposal, perceiving, acting, planning, and explaining a cognitive quartet with 4 neural networks. Imagine you are watching a quartet. You could say that there are 4 players who are playing probably different instruments. For example, there are 2 violins, there is 1 viola, and there is 1 cello. Those different instruments might also have different levels or patterns of sound. For example, the 2 violins tend to give high-pitched sounds, and the cello, which is the opposite, tends to give sounds of low tones. So each player could be either influenced or be influenced by someone else. However, eventually their sounds are merged together as a whole. That is more beautiful than the individual sound. In my research, I'm also interested in exploring how the different levels of cognitive functions like perception, acting, planning, and self-explaining could also contribute together as a whole so that they can lead to a more powerful intelligence. Sure. So now I will start by talking about the perception component. Perception is about how you understand the world. Let's say the robot is observing this mark, and the robot may perform a 3D perception like a point cloud. And the robot may also pay attention to some important parts so that it makes it easier to act in the world. And the robot could also go after to semantically recognize what are involved objects in the environment and what are the relations among those objects and how such relations could evolve over time. So for the acting component, when robots perceive the environment, the perception also triggers an action. And such action is primitive action. And if robot takes a sequence of such primitive actions, they can eventually change the world. For example, pick up this mark. Sometimes you don't have enough data to train, and sometimes you want to think in the long run, then you might need a model to do planning. With a model, you could grow a tree at a running time to find a locally optimal solution. And you may also have a symbolic description of the world as your planning model. And then you could find a globally optimal solution. And you only need to make sure that you execute each high-level action perfectly, then you can achieve your high-level goal. Sometimes you also want to self-explain the experiences that you obtained. For example, how you have solved the problem, what kind of mistakes you made, and why others could accomplish that task. And this is a type of metacognition, which is about how to be aware and reflective of your own learning. Let me show you an example to explain this. So let's say a robot is given a human demonstration. A human controls a robot to push a block to the yellow region, which is also L2, and the ring to the blue region, which is also L1. And then robot could explain to itself what are important information from this demonstration. For example, it can hypothesize that the location feature is more important than color feature. So in this new scenario, the robot may still push a ring to the L1 and the block to the L2, same as its understanding of the demonstration. However, the environment may tell the robot that what you did is wrong, is unsuccessful. The robot need to be reflective of successful and unsuccessful experiences. For example, it may observe that the regions of these two, the colors of these two regions are different. So it may update its explanation hypothesis that color feature is more important than location feature. So it may end up doing this, and then the environment tells the robot that you accomplish a task. So interesting is like a robot is speaking to itself, which could be what some could say that is a key characteristic of human level intelligence. So we want to use self-explanation to help the robot to gain some kind of insights. And such insights can be used to guide the robot learning in the future. So in my proposal, I want to explore a coupling of the four components, particularly first, how perception and acting can be coupled together, and how perception and planning can be coupled together, and self-explaining behavior like how we monitor and improve other cognitive functions. And specifically for the perception and acting coupling, I want to explore how robots can then test the perception knowledge from demonstrations to guide the learning of the acting. And for perception planning coupling, I'm interested in researching how plan recognition can be used to guide the various monitoring tasks. And also for self-explaining, we want to know if it can be like humans to be reflective and improve the robot's learning eventually. Hopefully, a coupling of such different levels of cognitive components can lead to a more powerful intelligence. So that they can accomplish more complex tasks and learn them better and faster. So all of my works can be put under the umbrella of cognitive agent learning. So we have three levels. One is subconscious level, and then conscious level, and then metacognition level. Perception and acting could be at the subconscious level. For example, in behavior cloning problems, we want to learn a direct mapping from sensory to control commands. Sometimes you also need to think in long term to drive your perception. For example, you do planning or plan recognition to improve the perception. And you may also think about what could be potentially applicable actions so that you can use such to make your perception more conscious. And for planning, it requires a model, and the model can be either from a human domain expert, like what we did in this work, or it can from learning, essentially learning from plan corpus. And for metacognition, I mainly investigated the self-expression behavior. And metacognition could improve lower level cognitive functions. And in my research, I'm focusing on the level between conscious and subconscious. Now I will talk about the first part, coupling the perception and acting, by talking about the work contrastive learning visual attention as affordance cues from demonstrations for robotic grasping. So what is the concept of affordance? Affordance is about the correlation among object, action, and effect. So let's say we have three different marks, they are in different shapes. So if you want to grasp them successfully, you may want to grasp them at different locations and maybe in different ways, so that you can reach to what is a desired effect, like lifting them up. So traditional work of learning grasping affordance from demonstrations kind of learn where and how to grasp from demonstration data. And where and how is essentially about control configurations that can be directly used by the external motion planner. for example, you have lots of demonstration data and you extract grasping orientations and you do clustering. And in this work, they cluster grasping pre-shapes. And with learned clusters, you can find the appropriate grasping configuration in the at the running time for motion planner. Now let me show you an example. In this work, so I'm selecting this object grasp. And now we are going to see some predicted grasping process and orientations, like these smaller green arrows on the object pointing outside. And then you input that to the motion planner, and it calculates the motion plan, and you are going to visualize the motion plan here. See? And this is a real-world execution by executing the motion plan. So traditional ways of learning affordance from demonstrations, they kind of separate the learning affordance part and also the policy part. Basically, it's a fixed motion planner and it's not learnable. And in our work, we want to combine the two directions together. One is the affordance from demonstrations, the other is deep learning-based imitation learning in end-to-end deep learning framework. There are many benefits. For example, the learning of perception and the policy can guide each other in a tightly coupled way. And our ultimate objective is that robots should imitate humans not only at the level of trajectories, but also their affordance test knowledge. So we take some insights from cognitive psychology. Basically, there is a close association between affordance and attention. So what does it mean? Let me use an example to explain. So let's say you are seeing two different kinds of marks. So if you shift your attention from one part to a different part, you may also take different kinds of actions in the future to pick them up. So we use visual attention to model the affordance cue, which is the affordance test knowledge. So now robot is given two human demonstrations by grasping the two different marks in two different ways. So to the affordance cues, we want the robot to explain to itself what makes the two demonstrations different. And then robot may discover that it is a handle or the body that makes the two demonstrations different. And handle and body are salient features. So inspired by this example, we built our framework based on contrastive learning, which can learn general features by teaching a model which two data points are similar or different. So let's say we have 3 categories of demonstrations. In each category, the human controls the robot to grasp a mark, different marks in a similar way. And for 2 different categories, the way to grasp it would also be different. Then we can learn embeddings that can be easily separated in an embedding space. So we extract affordance relevant knowledge, like when robot starts and finishes interacting with an object, and then we learn an affordance embedding, and we use this to guide the learning of observation embedding, which also gives the visual attention, which is affordance cue. So now let's say robot has a trajectory, demonstration trajectory, and here is an interaction segment, and we get an affordance embedding here. And at each step, we have an observation, and then we get an affordance cue, and then we use affordance cue and to get the observation embedding, and also get the policy model to predict an action for the current step. So we want to use the learning of affordance embedding to guide the learning of observation embedding. To do this, we propose a coupled triplet loss to this. And we also have a behavior cloning loss, which trains the robot to minimize the distance between predicted action and ground truth action. And by summarizing, by optimizing the 2 loss functions together, we can simultaneously learn affordance cues and grasping policy. So here is 2 video demos with our 4 model. And in this model, the robot focuses on the body and the grasp by body. And this video is more interesting because it corresponds to the affordance attention association observed by cognitive psychology perspective. So you initially say, pay attention to both handle and body, and then robot shifts its attention to the handle, and then the robot also picks up by handle. And there are two baseline models. One is that we don't use contrastive learning, and we found that our model tends to focus on all the marks by only on their handles. So the robot may not even take such affordance cue as guidance. And in this case, we don't use our proposed coupled triplet loss with normal triplet loss. And we also found that the robot tends to focus on all of the marks similarly by focusing on the entire mark. And this is the grasping success rate. Our full model with coupled triplet loss achieves the highest grasping success rate. So here are some takeaways. Because learning affordance from demonstrations have benefits of avoiding label-intensive affordance label collection, which is why we build our model based on such works. However, it would be even more promising to replace their external motion planner with a learnable policy. So we combine two directions together. One is learn affordance from demonstrations. The other is deep learning-based imitation learning. And it will also be interesting to consider multiple levels of interactions that drive even more expressive affordance cues. It will also be interesting to apply our coupled triplet loss to other robot learning problems. So why the affordance cue learning made the perception more conscious, but it's still model-free and does not think in long term, which is what I want to solve in the next part by learning a shallow domain model for planning. So it's more at a conscious level. We use learning to learn a model, and it uses a model to search for a solution for planning. So I will start by talking about what does the shallow planning domain model mean. So by comparing it to similar concepts. So if we have a fault planning model, we can use search to find a globally optimal solution. And sometimes the planning model is incomplete. So the solution that you search cannot be guaranteed to be optimal. So, but the solution is still approximately correct. And sometimes you even only have a curvative model. It's not even, they cannot even be used to directly find a solution, but you can still use that model, what you found from by using such models to guide the planning. And what I want to focus on is this. Sometimes you don't want to define a model on your own. Instead, you want to learn model from data like plan corpus. So you learn a model from data to get a shared model for planning. The data will be like this. Such data can be a sequence of actions that can be obtained by running a classic planner. And you may also observe that this is a symbolic sequence of symbolic actions, which are also similar to a sentence in natural language processing literature. So this inspired us to ask, can we use some NLP techniques to solve our planning or plan recognition problems? So what is a plan recognition problem and why we can use planning to solve them? So let's say here we observe an incomplete plan. There are some positions that you don't know what was happening, what was the actions that was taken. So you want to recognize the plans. So you use the learned model to search what could be most likely actions, and you put them here to make the plan complete. So we borrowed two NLP techniques to learn shallow domain model. One is order embedding techniques. The other is recurrent neural networks. However, the previous approaches have a problem. They assume that the input of activity sequences are deterministic. However, such activity sequences could be recognized and provided by a visual recognizer. And such a visual model might suffer from errors. And if there is an error, the plan recognition module would have zero chance to say the correct action. For example, if the visual model outputs a recognition distribution like this, and the traditional way of plan recognition will take this action, which has the highest confidence or probability value to be correct as input. However, if the correct action is this, then the plan recognition module will not see this action. So we want to learn a shared domain model from the entire distribution sequence. And the problem becomes this: we learn a shared model from such distribution style inputs. And then we have an incomplete plan like this. And then we use this model to do plan relation to figure out what should be the actions to be put here. And we evaluate our model according to different levels of perception errors. And we found that our model, which is this gray color, performs best when perception error rates are high. And when we have lower perception error rates, our model performs comparably to baseline models. However, this is a training time curves. Our model performance requires almost the same training time to the simplest model, simplest baseline model based on order to vector. And another baseline model has a linearly growing training time. So we can draw the conclusion that overall our model has the highest value. So in this works, we bridge a gap between plan recognition and visual recognition by learning embeddings from uncertain inputs. However, can we use such learning model to use plan recognition to support the perception? Which is what I'm going to talk in this part. So you learn a model, shared domain model, and then you use a model to do planning or plan relation, and then to recognize the perception part. So what would you focus on when you see this picture, which could be captured by a surveillance camera? You may focus on this area because you may internally recognize the plans of the two policemen, and then you focus on the region that could have a very interesting activity that can happen in the future. So your mental procedure might be this: you focus on the moving object, and then you recognize their plans, and then you may also pay attention to where an interesting event is more likely to happen. So what we want to do is how high-level plan relation can also improve low-level perception. It could be challenging because plans could be discrete symbolic actions. However, attention could be pixel-level probability maps. So how to connect them together? I will start by talking about how to train a shared domain model for plan recognition by using our techniques like distribution to vector or word to vector. So let's say we have an observed action distribution like this. And now you are given a video stream. And for each 2 frames, you extract frame level motion features like frame difference or optical flow, and you do clustering, and you get a library of clustered features. And then you see a new video, and then you also similarly you get such features, and then you compare the distance between this feature and all of the feature vectors in the library, and then you take, you know, what is the closest cluster central to this feature, and then you can get, for example, top 3 closest actions. And you also approximate the observational uncertainty by using such distances. And you move to the next frames. However, you know, in videos, an actor like a human may move slowly, so that the order of these 3 actions, if they are ordered according to probabilities, their order might be same as the actions that are also ordered in the according to probabilities. So if they have same order, we want to temporarily merge them together. And then you can collect plan corpus from such observed action distributions, and then you learn a shared domain model, which allows you to do plan recognition. For example, you have a new videos, and then you similarly you obtain the 3 observed action distributions. You learn the model to do plan recognition, which gives you 3 predicted activities in the future. And then for each activity, we want to learn an attention map one by one. And each attention, for each pixel location, there is a probability which tells how important that region is for an event to happen. And then because we care about where could be an interesting event to happen in the long term, so we summarize these 3 probability maps, attention maps together to get a plan recognition driven attention map. So here is the overall architecture. At each step, we have an observed image, and we have bottom-up attention module to give a bottom-up attention, and then we mix it, multiplicate it with plan recognition driven attention, and then we can improve perception. For example, we predict what could be an event that can happen in the near future. And we also use such attention to do plan recognition start from the current step. And then we update the plan recognition driven attention map. And then at the next step, we have a new observation, and then we use this PRD map to replicate the previous procedure, and so on. So our baseline model is a purely bottom-up attention model, and this is our model. And this is a visualization of attention map. So these are predicted glimpse by using bottom-up attention model. And here is a bottom-up attention. And here are 3 steps of plan recognition driven attention. So intuitively, we can improve perception to improve planning, which are what most a lot of people have been doing. However, in this work, we ask the question if we can use plan recognition to also improve visual recognition. It's essentially like how to think ahead to better see the present. However, can we use even higher level cognitive modeling like self-explaining to improve perception and other cognitive functions? Which is I will talk about in this part. And I will mainly talk about this paper, learning from ambiguous demonstrations with self-explanation guided reinforcement learning. So sometimes we want agents to be reflective of their own learning. So agent could gain insights to guide their learning. So for example, they may have some failure experiences and also some successful ones by observing, for example, human teachers. And such insights can be used as a learning guidance for the agent. So sometimes when the successful experiences are from human teachers, we also need to have a robot to better learn from humans. So intuitively, we want a robot to think at a similar level to humans. So we could give a robot some human relevant background knowledge. So when robot takes human advice, for example, let's say robot takes a reinforced learning agent to learn from human. And sometimes in some challenging environments, it's very easy to give ambiguous demonstrations. So we are solving a reinforced learning from ambiguous demonstrations problem. And because reinforced learning works by trial and error in the environment, so in the beginning of the training, most of the samples might be failure ones. So robots have some failure experiences and also successful ones from human demonstrations. So we want robots to self-explain with the human-related background knowledge. by getting some insights to guide its future learning. So how to guide? We have two ways. One is to augment state. The other is to augment rewards. So what is a self-explanation? I will start by talking about what is a human-related knowledge. So it's about robot knows what are important relations in the world in the form of predicates. And robot also knows how to detect such predicates with an observation. And then robot, the explanation is about which predicate is more utilizable to explain why a decision making is important as a step. So robot could explain that for example, robot may want to push a ring to the blue region in L1, and the robot may hypothesize that the color is more important. So robot may focus more on ring at blue predicate. And it keep focusing on that until this step. So to augment the state, we basically append the predicates and the utility weights features together with the state for reinforced learning. And to augment rewards, we construct the reward shaping by dot producting utility weights and the predicates values. So the first task is a simple robot push task. In this simple task, we don't include the L1 and L2 in predicates. And in a more complex robot push task, we have both color features and L1 and L2 in predicates, like this. So it's a simpler task, and robot hypothesizes that block at yellow is more important. And then it also, at this step, it also explains that ring at blue is more important when it pushes the ring to the target region. So this is a more complex task. At this step, robot hypothesizes that ring at blue is more important. And later, because there is only one free spot, robot does not need to distinguish between blue or L1, L2, so it can focus on both. And there are some baseline models. So this is not a baseline model. This is two other different ways to use self-explanation to help reinforced learning. This is a case that you guys are seeing the slide 91, right? Okay. So, and here is a new task, which is more complex, pushing and remove and pushing task. So in this task, there are two objects. And if the object is initially located on the left part of the table, the robot needs to remove this black cover and then push it to the target region. Dr. Rao, are you seeing the slide 93?
Yeah, we are fine.
Okay. So in this more complex task, robot still is able to explain that the blue feature is more important. And similarly here, yellow feature is important, and it pushes to yellow. And in this case, robot figures out a smart way to remove the black cover and push it to the target location. And also it focuses on the correct color feature. And here is the Pac-Man experiment. So basically, the Pac-Man needs to avoid being eaten by the Pac-Man. However, when the Pac-Man is kind of close to the ghost and also close to the pellet, Pac-Man could eat the pellet, which allows the Pac-Man to also eat the ghost, then it wins. So here is a demo. So originally, when ghost is nearby, which is what Pac-Man is caring about, it tends to eat this pellet. So, and once it has eaten a pellet, it cares about if it can eat a ghost when the ghost is nearby. So here are the evaluation results. So the blue curves is a baseline model to delay the DDPG and solve the actor critic and solve Q learning from demonstration. And we have 3 ways to use self-explanation to help reinforced learning. The red curves are our full model, which uses both ways to help reinforced learning. And the aqua curves only use self-explanation to augment the states. And the pink curves only use self-explanation to augment rewards. And we also compare our work to a baseline GAN-based inverse reinforced learning model, which does not use self-explanation. And we also have gray curves, which does not use task rewards. Because reinforced learning from demonstration, using task rewards is a very important assumption for such works. So in the simpler tasks, our self-explainer only helps train delete DDPG, and because of the lower degree of ambiguity, the software actor critical from demonstration performs comparably well to the self-explanation models. However, when we have more complex tasks, our self-explainer has both learning agents, reinforced learning agents, and similarly here, and also Pac-Man experiment. So our work actually obtains good reviews from conference on robot learning. It's almost a get in. So for example, this review says that it's an important problem and also interesting algorithm. And this review said that our approach might be used to benchmark future reinforced learning from demonstration works. And this review mentions that it's a very interesting problem. And it also raises score to accept, and it said that there are some interesting concepts for robot learning community. So here are the takeaways. We open the direction of learning to self-explain, which is essentially to have to let the robot be reflective of their own learning so that they can guide the other learning of other cognitive functions. And particularly, it's important for learning in more complex settings like environments that can easily lead to ambiguous experiences. It would be interesting to consider if we can explore self-explaining mechanism to help other robot learning problems. It will also be interesting to think about if there are better ways to learn self-explanations. And this is the main direction that I'm exploring. Conclusion. So the problem that I have addressed are the possible couplings among different levels of cognitive functions, like perception acting coupling. And in this work, we combine the directions of learning affordance from demonstrations and the deep learning-based imitation learning. And the second level is perception planning coupling. I focus on these 2 directions. One is to learn shared domain model for plan recognition. The other is to use plan recognition to improve real perception tasks. And the third part is how to use self-explanation to support the learning of other cognitive functions. So we focus on improving self-explanation from reinforced learning from demonstration problems. So right now I will talk about planning for acting by talking about a video demo that I have with Alaka on her explicable planning work. So because we use AR markers to simplify the perception problem, we really are focused on planning and acting. So in this domain, robot needs to deliver an electronic device and a cup of coffee. So from human's perspective, it's safer to deliver them separately, one by one. So, however, robot has lowered the cost by delivering together by saving some energy. However, from human's perspective, it's better to deliver to the device and the mug one by one. So here are my publication papers. So here is the thesis timeline.